Okay, let's get started. So the second talk by Professor Philip Kim, he will be talking about topology of atomic scale lattice reconstruction and van der Waals interfaces.
Okay, well, thank you. Yeah, so welcome back. So as I mentioned in the beginning, that second part of the talk is a bit tangential for the other topics in the school, but nevertheless, I think I like this topic because throughout this studying about this studies, I know it's a little bit of topology certainly. So that's this is one of the topics that forced me to the understanding topology so much. And also, I feel like that this is an important part of the physics that governing underlying this the van der Waals system, and the potential there is some of the interesting idea may comes around. So let's see that how it goes. Okay. Why? Oh, now it's okay. Thanks. Yeah. All right. So this talk is based on the many collaborations, and then I want actually especially that this two-person, Rebecca and Gilbert, just graduated, and we knew that was former postdoc now in the Sorbonne University, and with help of the other experimentalists, as well as a theorist, especially Stephen Carr in the Kashras group, was Kashras group, and Song Han on SKJU. And then, because it's related a bit of the topology later on, you will see that we have the rather interesting collaboration with this mathematicians, the Mitchell Luskin's group, as well as Minion Han and others. Okay. So I think I showed you this type of the figures that when you just put this two graphing layer together with this angle, there's a Moire pattern appears. And I just kind of mentioned in the beginning, you know, that there's a operative quasi-periodicity that we can use as a Moire periodicity modulating band with relatively large length scale, about the Moire length scale, something like this, few nanometers to the tens of nanometers, restructuring that. But if you just look at this kind of these structures carefully, of course, this is not completely periodic system. At the best, it's quasi-periodic. Right, except that twisting angle matches some of this very few discrete, some of this discrete incommensurate angle. Basically, lattice is largely incommensurate, right? And roughly speaking, that certain area that you have the AB like the stacking or BA like the stacking that connected with the invariant symmetries between them, right? And also this area that so-called AA stacking, all the lattices, they kind of on the top of each other, and they kind of constituting that this kind of quasi-periodic structures. And knowing that how that these atomic structures that plays a role is quite important to understand the underlying electronic structures, right? That's in a sense a low energy approximation of the Bistritz and that Macdonald model is kind of one of this. Very useful, but also powerful approximation at the low end sectors are very successful. But there, that simplest applications of the type 1 model with just kind of rigid rotations of these two, the beryllium zone, kind of basically missed out some of the important factors following, right? Imagine that this twisting angle is a relatively small, right? And then turn on the interaction between that. We know that nature, there is no exist of the AA stacked graphite, right? Part of the reason is that is very unstable structures, right? Nature prefers so-called bonus stacking, AB versus BA type of the bonus stacking, right? So simply that without any detailed calculation, if I ask that if the lattice is deformable, and what we expect here is, well, that nature will try to maximize AB and the BA type of stacking, and minimizing this unstable AA stacking, right? So you can quickly see that the unrelaxed structure that I showed you quickly relax with atomic interactions between these lattice and maximize the AB and BA and minimize the AA type of the structures. And that's kind of what is going on. And we want to describe what is the procedures of that and what is the effect of that. I think that's something we can do. In fact, that's kind of what has been seen in the nature. And well before the twisted bilayer, this is the work that's done in Paul McKinsey and several years ago, in 2013. So that's many years before even just the twisted bilayer stories, even any serious van der Waals central structures. But this is basically chemical vapor deposition grow the bilayer graphene, supposedly nice bonus stacked bilayer. But quite surprisingly, when they just look at these images under the TM images, they see that this is not a single domain, but alternating domain of the AB and BA stacking that contrasts with the TM images. And when they just use a different technique, which I'm going to show in a moment, just to look at these domain structures, there is a nice domain between them. It consists of high resolution TM images, slippage of this two atomic layer from AB to the BA. What it says is basically there's no crystalline defects, abrupt defect in both the top and bottom layer, right? And simply you just change it from AB stacking to the BA stacking by just kind of gradually changing the atomic spacing around this domain. And that's kind of what they call this the structure soliton. Later on, that this is basically in the structure language is the same as the dislocation, but nevertheless, that domain boundaries consist of the structure soliton, the dislocations connecting BA to the AB. And then if you just look at this lattice of the top and bottom layer, there is no topological disorder per se in the individual layer, right? So that has been kind of discovered, and you will see that this type of structure is basically kind of exactly related with what we are seeing in the twisted bilayer or any twisted layer system. Turns out that the way that you can detect this type of the structure manner is using the electron microscope. The transmission electron microscope. Transmission electron microscope shows that the electron is generating. There's electromagnetic lattice, the focuses, and the various lattices. Like the electron optics, like the real optics, that depends on the way you choose this imaging plane. You can get this diffraction images, T space information, as well as the real space information. In this TN column, that if you just use this aperture in the back focal plane, that basically you get all this diffraction pattern coming from the underlying lattice. So in this particular case, it's a graphene, twisted graphene on the top of the boron nitride. They showed all the black peaks. Especially boron nitride will give you substrate the brightest peak, but close by, but nearby, you can get the graphene peaks. If this two graphene lattice is a small twist angle between them, for example, the black peaks are very close by, so they appear almost kind of one peaks there. But you can just choose one of this black peak or the first order, second order black peaks. That will give you kind of the real space of the Fourier transform the images. So using that black peaks and only that is transmitted through the apertures and project on the image plane, you get kind of this momentum selected or Fourier selected the imaging. With a small tilt of the sample, you can just distinguish the AB versus BA stacking in that structures. So that's kind of structure matter. And basically in the images, you get this AB versus BA contrast by just kind of using this dark field imaging scale as the techniques. So that's kind of beautiful techniques. Also, you can just choose a different diffraction peaks. You can just also contrast this boundary model, which I'm going to show you also later. Anyway, so using this the dark field TM technique, filtered dark field TM technique, one can just look at this twisted bilayer and ask that, okay, so what type of the structures do we get and this type of structures? And obviously, as you just change it to twisting angle, your water pattern size got changes, and therefore you get the different type of this the structures appears. Say 0.1 or 0.3 of the twisting angle, largely away from your matching angle, but your water size becomes larger, and the scale here is about. This is about. is about 200 nanometer. If I calculate it really carefully. But so you can see that this water size becomes tens of 50 nanometers, even 100 nanometer length scale with a small angle, right? As you go to the larger twist angle, approaching to the or passing through the magic angle, then of course this pattern becomes small. But important notice that here is even if you zoom in there, you can see that the contrast between domain becomes weaker and weaker. And the contrast of the domain is related with the degree of the relaxation. The darker and the wider, or the more of the contrast, you get into more of the locking into the AB versus BA, which means that that as you go to the larger twist angle, there is less and less of the reconstruction is happening. Right. One way that you can see the more quantitatively is just to look at the diffraction pattern, not just a Fourier transform, but just kind of look at the rather than imaging, so you can just kind of take the diffractions. And you can see that as you go to the larger domains, basically the diffraction peak becomes kind of really close by. It's a bit difficult to dissolve it. Already 0.04 degrees where you have the large the resolution and the diffraction plane. You see that except that this two peak, there's multiple scattering peaks appears. And this multiple scattering peak, presence of the multiple scattering peak in the structure is related with additional modulation. That basically is related with this reconstruction of the lattice. Analyzing this multiple the peak and especially the intensity kind of tells you how much of the reconstruction is happening. What you see here is as you go to the larger angle, already 1.6 angle, besides these two peaks, their satellite peak becomes really, really big, right? Which means that that's basically not much of a reconstruction. Taking this bragg peak versus satellite peak intensity, therefore that gives you the good way that you can tell that how much of the reconstruction is happening. And as you see that as an angle of the twisting angle, as you go to the larger twisting angle, that the ratio between the major and the reconstruct peaks decays, and this is a lower scale exponentially, tells us that as twisting angle increases, basically reconstruction is quickly go almost exponentially, right? So, which means that there must be some characteristic length scale where reconstruction is really large, significant, right? In other words, what is, if this is the exponential decay, what is the characteristic angle that this is determined? And basically the slope, right, in the exponential there. It turns out that characteristic angle, the reconstruction is significant, is about 1 degree, right? And somehow very close to magic angle, right? We haven't figured out whether this is really something deeply related. At this point, we believe it's accidental, but nevertheless, it's kind of quite fun to see that 1 degree, the magic angle is again the angle that where you start to see that appreciable the reconstruction is happening. And this also tells us some of the important part. I know that yes.
I mean, there are higher magic angles as well in the system.
Yes.
Do you see again this reconstruction?
No, that's kind of the point I was trying to make. Good point. Right. The theory, this is the McDonald model that tells you there's not only first magic angle, the second and third and higher orders, right? And usually goes to kind of smaller. The second magic angle is something around 0.55 degrees or something, right? Turns out that's already very strongly reconstructed region. And which means that unless you just kind of consider that how this the relaxations plays a role and modify your theory, basically the distance and the McDonald model doesn't work too well. Indeed, some of my colleagues who did do more of this realistic type of calculation, including the relaxation, basically usually this the flat band structure, second magic angle can be washed away quite quickly. And move into the some of the other angle, we have to allocate such it out. So that's kind of already give us some interesting part. And then way that you can just kind of understand that is, okay, you can go through the realistic model, considering all these atomic scale of interactions. And as I mentioned that previously in the beginning, that the way you can just understand is AB or BA domains, basically you get this untwisted to get into the more of the bonus stacking. And that is compensated because the overall twist angle is basically fixed by the talking the AA degree more, AA area more. reducing that area size, but actually there's more of the rotations there. And that's basically what theory, the simple model tells you, that AB domains are getting to the more of this, as the twisting goes lower, AB domains getting to quickly getting to close to zero, or the Bonner stacking. AA talking is basically increase and increase more, or that stay constant, at least as the overall twisting angle is smaller, and that some of the torque is remained in the AA side. I think that's an interesting. Yes, go ahead.
You mentioned that the characteristic angle was about 1 degree, which is about the matched angle.
Yeah.
I was wondering if you looked at this for like, alternating like tri-layer cases, because the magic angle, the first magic angle is going to be higher.
Yeah.
And so you might see that correlation versus not.
Yeah. So that's a very good question. So again, the alternating twist angle, the matching angle is over 1.5 degrees. Right? So that's actually beyond that this characteristic angle of this between two layers. The reconstruction effect is lesser, right? So I think there is a small populating way that you can just correct that. So again, I'm not an expert of the calculation. There has been some expert of the theoretical way that you implement this relaxations already, quite a bit, I would say. So for this omega 0 and omega 1, that basically the type binding parameter between AA side of the tunneling versus AB side of the tunneling. And that kind of implement here the entire model, then take account a little bit of the relaxation, as long as your relaxation effect is not so strong. Right? So that is alternating to angle 1.5 degrees or around there. I think those kind of correction works kind of reasonably well. Right? Yes.
I think some of the audience probably said that they cannot hear you very clearly. Can you adjust the microphone?
Yeah. Okay, good. Hopefully it works better.
Yeah.
Okay. Okay. Now, I want to actually try to give you somewhat different approaches, especially now in terms of structures. Kind of holding models, it has a quite interesting part, intriguing part, also tied with the soft condensed matter, and also kind of reveal that its own topological natures into the structures. So I will just kind of present this picture in a slightly different way in following way. So let's look at the unrelaxed lattice, kind of the potential, right? The one way that also I can see that is instead of I just look at this in terms of the rotation, as long as I'm just kind of focusing on the really local structures everywhere, right? Already I mentioned that where there's AA side, the AB side, BA side, what does it mean is, well, although this rotation that I can map into the, if I just look at only the local area, look at this kind of shift structures, right? Shifted kind of one to the against the one to the other. That's basically the concept of the AB versus BA, ASB. So I can expand that all of this, the lattices, right? So I quantitatively describe that this displaced or the part is basically in terms of mapping the shift. In other words, I can just define so-called the lattice shift vector. This is again borrowing the language from soft condensed matter. And then the difference between the top and bottom layers that corresponding that without any twist. Right? So that's basically shift vector. But then obviously, because there is a more periodicity, it's better that we define the shift vector in the periodic unit. Right? I think that's an important part, and that's where then I want to bring this more periodicity or quasi-periodicity into the system, right? So it's a very natural that I want to map all the shift vectors that define the corresponding differences back into this the Y unit cell, which is basically period structures, right? So which means that in a sense that I have this two-dimensional the surface, the shift vector space is now sitting into the torus. So it's kind of considering this periodicity. Right? So in terms of mathematics, it's a kind of interesting mapping problems of this shift vector that define the 2D R2 into the torus type of the system, right? Let me just kind of visualize that a little bit in terms of the color, because it was shift vectors. I think again. So this is basically shift vector space. I just kind of give you that shift vector space with the any point in the color, and then you see that this blue color around this region is basically the same as blue color there because it's periodically connected between here to there and here to there. Again, this is a real space that kind of unit cell that periodic unit cell shift vector is lead. Unfortunately, I don't have the good color for the AB or the BA region, but that's basically way. And then you can see that the corresponding the area of this unrelaxed structures is basically using this mapping. Okay, so here that this is AB like, this is basically this region. This is AB like the BA like, and the mapping to be all of these things. So AB, BA like, AB like, that they all kind of correspond in between all colors mapping there. And point here is when you have this the uncomment the other than this commensurate lattice, this uncommensurate lattice, quasi-periodicity means that this color is uniformly distributed all of the here, or the intensity of this color map that map into the there is basically uniform. That all angles and all shift is basically covered by every time that this incommensurate lattice give you the quasi-periodicity. Right. Okay, so that is unrelaxed. Now the question is, if I just turn on the interaction between the lattice, right? So now there's a step, the tendency that I want to connect AB or BA step is more prominent. How this type of this mapping is changes, especially now that all the point that I just kind of the graph here is uniformly distributed into this the shifted vector space, how they got changes. So it's a real space and the shift vector space I call the configuration space, doesn't matter. Right, it's a uniformly distributed, as I said. Now turn on the interactions, lattice interactions, and they happen following it. In the real space, it's as I mentioned, that I just kind of expanded AB versus BA regions. That basically more of the right gray, the dark gray region is basically expanded, right? And the AA region becomes smaller, and then all the in between, so-called this the transition region, becomes and sharper towards the line, right? And the corresponding the shift vector space is basically ABBA becomes heavily populated, right? And the AA region of this four corner is depopulated, and that's kind of wide region. And transition region is reasonably populated. Right? So that's basically the point. If I just make this case extreme, such that let's say the ABA is the most that energy to get into the ABBA region becomes really large. Eventually, I will have the one point and the other point ABBA with kind of almost all populated, right? This region is all emptied out, and that is connected by these lines of this blue and red and green. Right? That's basically the contribution lines. Right?
Sir,
yes.
This is for fixed angle, right?
Yes, it's a fixed twist angle. Right.
And if you now stop from that picture and increase the angle or reduce the angle, how is it changing?
So this, if I change the angle, basically the size becomes different, right? And then the distribution got changes when I just kind of the changes in texture between these two lines. More precisely, that there is a stacking port energies. I'm going to kind of show you now. That if I just say the stacking port energy becomes bigger and smaller, and that will give you a tendency that AB becomes how it becomes large, and how much actually this line becomes sharp and so on. Yes?
Can I just check that in real space, what's happening physically is that the interatomic spacing is changing so that like the lattice itself is becoming distorted for each layer? Is that what's happening?
So spacing is not changing, but in a sense, it is kind of untwisted, as I mentioned. Right.
So different like domains are.
So basically, you have this AB domain was small, but now I think that that area becomes untwisted and make this becomes larger, and then all kind of the incommensurations. Let's say that the simplest mind, I will make the most of the area becomes AB, and still that there's overall twist angle is still remains, right? So all this incommensuration is kind of this commensuration is trying to sit onto this boundary between AB and B, right? Yes.
the thickness of the transition region as you change the twist angle? Is the thickness consistent? Does it shrink? Does it grow as you shrink the twist angle? Does the pattern get larger, but the domains get sharper? Is that sharper on a relative scale? So how does it change?
So that's again that the length scale is all kind of fixed here, right?
Yeah.
And then this width, or okay, this domain size or sharpness of width actually again depends on the stacking forward energy scales. Usually, it isn't unless that ABBA is infinitely preferable. There's always kind of some of the finite thicknesses, and practically in the graphene typical conditions, that thickness of the domain width is several nanometers, right? Okay. So in some sense, another way that I can view that is the size of the domain becomes comparable to the width of the domain wall. Basically, the reconstruction is not happening, not preferable. Right, so that's good. Yes.
Professor. In the bottom diagram, we have a configurational space, and there's a lot of discrete white regions that are roughly interrupted by dark regions, especially in the fully relaxed plane. Yeah. So, first of all, what is the physical meaning of the white region, and what can you?
Yeah, so I think that this is kind of another good figure. So I think I was trying to plot into the 3D distributions, but if you just look at this one in following, this the number of the dot is basically the density of the distributions there. So it's not completely relaxed yet, and that's why small number of this one is close to AA regions, right? So if you look at the 3D distribution, basically you have the tall towers here and B, right, and connected by the ridges of the transition regions, right? Empty out most of the regions. So that's kind of the way that we can just number of the dot is basically kind of related with the density distribution.
And secondly, you mentioned this configurational spaces leads to population. Like in this case, the population of what?
Populations of so here that if I just make a grid of this real lattice, right? Each of okay, so if I just follow all these atoms there, right? Each atom will contains give you the one U vectors there, right? So if I just say that, okay, so if I just kind of connect with this small area, how many atoms give you the U vector correspond to this vector? The U vector, how many atoms in the real space give you the U vector onto the spot, right? So I can make the distributions in that. Yeah, good, great.
So
yeah.
Is the 1D stripe in the system correlated to the electron state?
1D stripe.
You can see that there is a cross triangle.
Yes, sir, this one. Yes, even for the graphene, bilateral graphene, we will just get the point. Okay, good. Well, I like it. A lot of questions. Except that I cannot make this one go anymore. I don't know why. Oops. It says that June, the meeting has ended after 40 minutes of the idle time. That's why it got stopped. What do you? Can you check? This computer is out of Zoom now. Anyway, so while you're figuring out, maybe yeah. Okay, good. Yeah. Another session. Okay, good. Now, this doesn't have to be in graphene, by the way. I think that's kind of a point. Any Van-der-Waals layer that if you just kind of stack them together with some twisting angle, they tend to actually develop this type of domains. Right? This one is tungsten diselenide with small angle. Of course, we don't have good angle control, and then often this is the kind of typical pattern you get that whether there's not a good control angle, there are kind of some ugly domains, the reasonable domains everywhere. So I think this kind of something happens when you just put them together, the bilayer graphenes, or bilayer, when you just put the two Van-der-Waals system. But turns out, in fact, it doesn't have to be even just the stacked system. As I mentioned, the Paul McQueen's original experiment was on the CVD ground sample. And this is a yet different sample. This one is a different way of producing the bilayer graphene onto the silicon carbide. And people have reported, and those kind of the structures that they're everywhere into any of this system, right? In fact, this is kind of interesting way. The people that did this experiment, the material scientists, actually describe somewhat different languages about the structures I'm just describing. Now that this more patterns of this domain boundary, as you see here, that they call this is a dislocation, right? I will just kind of tell you why that this is kind of closely related with the dislocations. But what I'm just trying to claim here is whatever this domain relaxation, especially after relaxations, that when we have the domain and this domain boundary mode, we can just use the languages already developed about the dislocation to describe that the structures we have in the system. So that's kind of the point. Of course, the dislocation is one of the important topics in the material science for a long time. In fact, actually, it was an important topic of the physics as well. Very practical importance, like the metallurgy, that the strength of the steels and all these metals is governed by how you just think the dislocation network, right? In the physics, of course, the dislocation as a topological defects plays quite important role, not only condensed matter physics, but also, say, energy physics and cosmologies. And then when there is a non-equilibrium sets in and kind of frozen into this topological defect, often plays a very important role into the structure. So it is kind of very important subject in some sense. Dislocation is topological object in the following sense. Dislocation carries some of the topological numbers, and that is what we call the Borgus factor. The way that we can just look at this dislocation is if the dislocation line is passing through a solid, if it's a constructed dislocation on the circle, circuits around this dislocation line, and you will find out that there's incomplete, the circuits appears to make this circuits by following to the perfect, compare with the perfect lattice. And this the deficiency or excess of the vector corresponds to the one lattice spacing. So what we call the Borgus vector, and depends on whether this direction of the Borgus vector is aligned or that perpendicular to the dislocation line. Often that we can call this is sort of dislocations and edge dislocations or mixed dislocations. And there's kind of languages that we can just utilize. And another important thing that we have to remember is that dislocation as a topological defects cannot be created or annihilate inside of the solid. Always the dislocations should end at the surface of the sample. And dislocation carries this, the constant Borgus vector, dislocation line, all the way is constant as long as the longer dislocation. Right, so that's kind of important. Quick run through about the dislocation. Now, dislocation, as I said, is important in the materials. And in the 3D, of course, this dislocation, as I said, is related with the stiffness and the strength of the solid, and how to just kind of make them creating this entangle this dislocation line becomes kind of very important. One part is because of dislocation is continuous, when two dislocation line meets, you have to need really careful down. It turns out this is still a very active research area into the material science. How when this two dislocation line comes and how they come through each other and what type of structures interaction is happening. That is a rather the intriguing project. But all these things, I don't want to go through that, but I want kind of mention following. If all these domain structures I mentioned is indeed dislocation line, and if I was talking about these domain structures in 2D whatever system, the one thing that's important that is the reduction of the dimension. Is basically we are talking about dislocation line network in the 2D, right? Which means all the dislocation lines are embedded in the 2D, therefore they cannot avoid each other, right? Unlike the 3D cases, the dislocation line can avoid each other making the structures. Now you force all the dislocation line in the 2D, they must cross each other. And as I mentioned, crossing this dislocation line is another complicated the matter, right? What I'm just kind of trying to claim here is that like the dislocation is topological defects, the junction of the dislocation line and crossing of the dislocation line, what it say by the way, AA side is also topological object, which actually carries its own interesting things in there. Right. Okay. First thing, can you just look at this dislocation line in the experiments, right? Domain boundary is a dislocation line, but can I just kind of really assign a Borg vector associated with this dislocation line? Indeed, we can do that. In the experiments, again, the original the Paul Macking's group showed it nicely just to show that how it works. If you just use the so-called second order diffraction peaks and imaging that with there, it turns out which graph peaks you just choose for second order diffraction. First order diffraction will give you a domain contrast. Second order diffraction peak shows it turns out two dislocation line not associated, selected selected the lattice. Right? In other words, by just kind of taking this second order diffraction line onto three different vectors, one can combine that those kind of second order diffraction line tells you that what is your Borg vector associated with this domain boundary, and we can also show that this domain boundary is nothing but location line in the embedded. Right? With that, what has been seen that is, in fact, this twisted layer, like the triangular lattice we did see. Indeed, the domain boundary is a dislocation line, and dislocation line characteristic is screw dislocation. Right? Turns out, depends on the domain shape and how it was created. The characteristic have changed. Sometimes it doesn't have to be the screw dislocation, but it can be anti dislocation, it can be mixed dislocation. They already figured out that it all kind of depends on the domain shapes and how we create it. Right? What is the implication of this? We can just do the same thing onto the twisted the system. Again, this is a very nice part of the twisted bilayer graphene. You can see that ABBA domain boundary is there, and if you just zoom into this domain boundary, indeed, along this few nanometer, about 10 nanometer length, a few nanometer length scale, there's a slippage of this atomic resistance, showing that indeed there is structure dislocation, structure soliton, or in our language now, dislocation line pass through, and this dislocation is, as you can, the dislocation is basically screw dislocation characteristic, meaning that along this dislocation line, lattice tend to slip towards the perpendicular directions, right? So there is basically this mismatch between the top and bottom, so that this is the shift between these two lattices. That's kind of what you're seeing here. So we see that there, yes.
I was wondering if there quantum Waals study on.
We'll see that. Yes, yeah. So at least at this point, kind of look like that reasonable that we have the twisted bilayer. Structurally, I can say that there must be some sort of collection of the dislocation network at this junction, and they created this kind of lattice, right? Okay, what is this structure shift? What is the nature of this dislocation, this junction, right? Must be some sort of topological structures there, right? What is it? Right. So we can kind of, let's look at this part. So here that I want kind of now bring back to this languages that we use as this configuration space, and let's kind of discuss that in depth, right? Let me call that, okay, so this is AB, BA, AB, BA, and getting to this stage, I have to cross this dislocation line with the Borg vector, right? And if I just kind of construct one of the circuits here that's surrounding this junction area, I should be able to get this some sort of, if this is something, that out of the circuit, I should be able to get some quantities out, right? Again, think about the one dislocation line to get the Borg vectors, which is related with the topological the quantity. I have to surround it, the dislocation line with the circuits, and that will give us Borg vectors, right? Likewise, in here, by surrounding this, I should be able to get, right? Let's look at this, how the circuits look like in the configuration space. It's a little bit more complicated, but let's say the AB and BA is basically corresponding to my configuration space or not, AB versus BA, right? I simplify that lattice is completely relax. So everything is just kind of 2 point, right, and connected by this line of this location line, right? So going from the AB to the BA, here to there, and crossing that one of the blue dislocation line, which means there are many different ways that I can move from AB to BA. But since I'm just crossing this dislocation line, I will choose a path AB going down here, shift it here to the BA. That's basically what happens in use, right? And then from the BA to the AB, I'm just crossing the red line. So BA to the AB, I'm going to the red dislocation, right? And same way that you can just do that. And if you just kind of following that along this circle, basically, that I'm just passing through that this pathway in the configuration space in the ASM. And you can just kind of use this mathematical structures there, right? Basically, it turns out this type of the geometry has been kind of well described in the topology language, algebraic topology languages. If you use a kind of free groups with 2 generators, and generator is basically either consists of this one of this the G move and the inverse of minus B move and so on, that you can just kind of describe this type of a circle with the 2 generators, right? And surrounding this circle, basically the AA region, basically give you characterized by this type of the element, the minimal elements. Turns out this type of the descriptions give you that this location or this line is kind of a vortex, but unlike this really you one type of vortex where the integer number is associated. Basically, this type of this vortex has the characteristic of the non-abelian characteristic, right? So that's basically kind of what has been kind of discussed. Because of this topological object, in some sense, you can create this vortex, non-abelian vortex, non-abelian anti-vortex, and dipoles, and polar poles, and all of the structures can be kind of constructed by just kind of manipulating these locations and make their junctions around together. Okay, so in this language, therefore, what I have here is basically when I have this twisted bilayer, basically I have this location network, or the other way that I can just describe here is basically this is an array of or triangular lattice of this non-abelian vortices and connected by this location between them. So that's basically the languages we have. Okay, long story short, what is the important implication of this? Basically, implication here is, okay, so this as a topological object or topological defect itself, if I call this is the junction point, the dislocation junction, I cannot create or destroy it without having this counterpart, or only the way that I can get rid of that is basically drive them out through the surface of my set, right, or boundary of my set. Right? So number of this type of the junction is kind of fixed, and that density or the number is basically determined by size of the smaller pattern or this density or the twist angle between them basically fix this number of the dually arrived topological defects. Yes?
Can you briefly explain why the 2 generators do not convert with each other?
Because they consist of the different type of the things, right? They are not right. So basically, RL versus RR moves basically corresponding to the different pathway that I'm just going to go through. It's a kind of distinguishable pathway we're going through. So
yeah, I was trying to imagine the same way on this slide. It's like if you apply R and then you apply L versus you apply L. Right. And R kind of looks the same to me, but I didn't go the whole lattice in my.
So let's see then. If I go to the RL, if I go through like this and go through like this, right? So I think that's a correspond to the
or maybe it's not the same for the larger structures, and when you're on the smaller structures, it might convert. I don't know.
No. I think that's I thought I figured out, but then I got confused when you asked. So all L versus L, why they are not the same? So that's related with I'm asking that this guy consists of this versus. Well, let's figure it out later anyway. So yeah, I don't want kind of the dual tone to the math. But let's expand this one a little bit more because I think it turns out this is only kind of I discussed about twist, but generally any two lattices if you just put them together, and then if we just kind of give you any of these relative strains, right? You're basically dealing with this 2x2 matrix of the strain, right? And going to the very similar arguments that I just mentioned about the twisting, you end up with all this kind of the relative strains basically decomposed into these say few different components. For example, isotropic versus the shear versus the uniaxial, right? They all kind of this deformation and to create this model then, right? But then going through the same relaxation phenomena that we end up with is the network of this location or this arrays of that, right? And then you can ask that, okay, so I will have this say similarly network the arrays of the non-abelian vortices here. Simple thing, by the way, is that if you have the non-abelian vortices, you can have the anti-vortices somewhere. So one way you can think about is if I just twisted the one direction, going to the twisted opposite directions, I may be able to create the anti-vortices. Turns out that's not the case. They all create the vortices, including the isotropic expansions. Non-abelian vortices array only appears when you go to the uniaxial of the shear lines. Right? So in the end of the day, that we can create this combination of the vortex and anti-vortex array here by just kind of creating just kind of the distribution of the different relative strains into the system. And that's a way that you can create this rather complicated kind of structures into the system. And even just to create this the network of the combination of the vortex and anti-vortex arrays. So that means that by doing the substrate engineering, there's a possibility that we can encode those kind of structures in here. Okay. Indeed, if you just look at the sample, many cases you can see that there's arrays of the vortices or anti-vortices. If you have this non-uniform strain distributions and competing strain distribution, you can even just kind of look at the vortex. I can show that the RGB circle and anti-vortices kind of vortices with some of the separation fixed by some of the pinning between them, I guess. So there's a possibility that we can create those kind of structures. Right? Okay. Is this really useful other than structure? So that's kind of somebody's already started asking that. So let's kind of go through some of the aspects that one is useful things about. First of all, electronic structures. This can be very important part and most of the related with the other part of the system, but let me just put idea a little bit here. So when I have this domain of the AB and the A and AA side, if I apply the electric field and say it, when the reconstruction is really strong, such that AB and DA are rather close to mono-stacking, simplest mind is apply the electric field, we can gap up this AB and DA, right? Leaving this domain boundary is gapless. However, if you just look at the bilayer monostack, the band structures applying the electric field, applying the electric field to open up the gap in the AB domains with positive. Turns out if I ask the size of the gap, BA then is opposite side. So mass of this gap is changing across this domain, which means that this domain boundary mode is topologically protected. Right? The calculation shows that when you have this gap opens up the ABA BA by applying the electric field, this domain boundary mode is topologically protected again. The mode actually remains, and this topological protections give you the two counter-propagating states that this value is polarized according to this definition. Right? So in principle, that if I have this type of system and apply the electric field that get out the system, I leave with so just the domain conduction mode, which is kind of repolarized with the value. Right?
Sorry.
Yes.
Is it possible to detect it through the transport?
Is
it possible to detect that through transport measurements?
I'm going to kind of argue that. That's a beautiful argument. Yeah, but there is some of the signatures. Okay. So what do you expect? Okay, so this is basically kind of value polarized on these states, right? And then in fact, actually there's two copies of them. So if I ask that, if I measure that this domain transfer mode, that should be about kind of 4 scale age of the conduction in terms of it's about 6.5 kilo ohms of the resistance there. Indeed, there is a FEM 1 group's measurement. I think this paper is showing that if you have to separate this 1D ABBA domain boundary, they demonstrate that they can measure about this type of quantity. Right. Now, next question is, can we take that into the really 2D type of method? Right. I will argue that kind of following simple case. So if I have the bulk ABBA domain boundaries in that way, right? It's all kind of ABBA and the boundary mode, they're all conducting. Then basically it's a kind of twisted biology conduction, right? Now let's apply the electric field and gap out zero, right? If the gap is very, very strong and large, right? And then now I just leave it as the domain boundary, right? For more, let's forget about that the junctions. Basically, all this resistance is incredibly small, right? So in other words, in that simple model, this is basically a network of this quantum resistance connected to the triangles, right? Now this is a good undergraduate homework problem. Triangular lattice with this resistance. What is a 2D resistance? It's the same resistance, right? Square lattice and triangular lattice basically they give the same answer. Right. So one way you can detect that is indeed can we see these type of things? Indeed, there is experiments one can just do. So this is basically bonus stack by layer, top and bottom gates, as I think that I showed you somewhat similar before. Along this is a charge neutrality point, which is our interest, right? Applying in this side and this side, basically you get of the displacement field, the gap opens up, and that's why the resistance becomes higher. And if I just cut through this different line like this, right? You see that as you go to the larger displacement field, this peak becomes a larger resistance, showing that actually gaps are increasing as expected, right? Now let's go to the other bit larger twisting angle, 2.8 degrees. Critical angle or the twisting angle is about 1 degree. 2.8 degrees is already much larger than this angle, critical angle. There's not much lattice reconstruction. There's not much torque between them. So almost two independent the graphene layer, right? So there, that I expect to see that they basically independently flow through the Dirac point, the current, right? So there's basically two Dirac points there. As you just change the displacement field, you go the one Dirac point and the other Dirac point. So you expect to see that near this 0 and 0 displacement field, you get the most largest resistance. As you move away, basically you get lower conductance, right? So that's kind of basically what it is. If you go to the sum of this smaller twisting angle, smaller than critical twisting angle, where that supposedly that the interaction, the reconstruction becomes stronger. Applying that this same direction. First of all, you see that there's a multiple peaks appears. That is coming from basically Moire structures I just mentioned, right? The much larger. But then when I just look at this again, that the neutrality point follow through displacement field, basically it doesn't change it too much, and the resistances are kind of close to the order of the 6.5 kilo. Right? Turns out that indeed, roughly say that it's not fantastic the demonstration, but idea that I just present about this network of the resistance seems to work here. Right? I mentioned that this is not fantastic because, in a sense, I just kind of think about the equivalent sums and not just kind of really coherent connections between them. Indeed, theory tells us that what is expected if you just get another equivalent sum, there's a rather complicated pattern appears. That what is when you just live with the 2D network of the system, what is the RxX and RxY? Actually, that is a very interesting question. Both theoretically and experimentally has not been answered. Theory actually just look at it as a state, but they didn't give us that what is RxY that should look like, although this is triangular chocolate coding model, but important part is it is a helicity in between them. The best we can do that is applying the magnetic field. We see the rather complicated diagrams, and there's some of the structures there. For example, is there's too much disorder to say something about this kind of network, but certainly this would be interesting observations for the experiment that we can do. And I hope that some of you may actually carry over this type of experiments. Furthermore, it could be very interesting that not only just network, but selected out one of the layers there, right? One of the points there. I think if you go to the lower twist angle, you can get this type of structures. You may ask that, okay, now if I send the electrons through the topological defect, how they will scatter off, right? If I just close one of them again, do I expect some of the phase shift? What is the phase relation between them? I think these are kind of all of the interesting questions need to be answered, but kind of quite interesting. Is this really related with magic angle twist bilayer? The answer is probably not likely at this point. Part of the reason is, as I said, the magic angle is right at the verge that this relaxation becomes kind of important, right? So when we apply the electric field, usually that this type of the strong effect, that gapping out A, B, and D domain does not seem like develop here, right? But certainly, this type of physics becomes quite relevant when you get to the smaller twist angle, such that relaxation becomes quite important. How much time do I have? 5 minutes, okay. So, second example I'm going to discuss is really quick because of the lack of time. But certainly, it doesn't have to be interacting. We can go into any of the other twisted system, go to 0 angle and 180 degree. They start to form the different type of. And this type of domain formation and different network again can be understood by setting that I just kind of this configuration space argument I just use, right? And then turns out that actually underlying flows is even different. Here is a generation 2, although I have to prove it that still. This is related to generation 1 table and different descriptions. Moreover, if you just break this the lattice metric linearly like the traditional method H phase where there is no inversion symmetry into the lattice, by stacking this one, not only you get the domain, but this domain has to develop this common dipole moment across the structures. For example, that the 0 degree connections of this TLD materials, there are the polar domains that form, which means the ABBA domain is related with basically their dipole ranges, which actually affect their optical properties, as well as more exciting part is they will give you the network of this. Let me skip this one. Network of the ferroelectric domains, right? And which actually can be tunable by the applied electric field. It turns out to understand this network domain, let me just kind of skip this one. It turns out when you apply the electric field into the system, you can change this network domain structures. But here the topology plays a kind of very important role in following way. Inside of this is where kind of design the domains, right? Here that this junctions of the domains or junction of the domain boundary is I just mentioned as a topological defects, right? And their number is fixed by the average twist angle. So unless you just twist this angle globally, basically, I cannot get rid of any single of the disjunctions inside, right? Which means that even if I supply a very strong electric field and try to make the one of the depolarization domains try to win, I cannot get rid of the another domain completely, right? So in a sense, this is kind of give you some of these protections about the antiferroelectric the domain configurations by just particular these topologies innated from this junction area. However, that picture got changes when I can get rid of this topological defects. And how can I get rid of it? Unfortunately, here is everything is just one type of the topological defects, right? There's only one type. Vortices without vortices. However, you can go to the edges, and edges basically I can drive out some of this domain the defects, right? By doing so, I can make this kind of edges can be completely switched from one domain to the other, right? That's basically because at the edges where I can just kind of nucleate the kind of make the creations of the annihilation of this topological defect is possible. With this one, basically what we can say that is, let's see all these things. Another application of this is so this is basically the last slide I want to share. Is basically controlling the twist angle and controlling this kind of the topological the configuration of the junctions. Basically, I can create sometimes it's more like the domain anti-ferroelectric arrangement up to that kind of ferroelectric arrangement, or that just a dielectric response if I just kind of control the twist angle beyond this critical angle, characteristic angle. And this is basically completely possible into the system. And this is another interesting application of the topological nature of this type of domain structures. Okay, I think that's all kind of I want to say, but let me just kind of make the one closing remark here. So in the first lecture, I just tried to give you that the connection with the topology, electronic topology, band structure topologies into the some correlated insulator superconductor we are seeing in this twisted layer system, especially multi-layer system. In second lectures, I'm just kind of saying that this twisted structures that provide us yet different type of topology, especially it's related to its atomic configurations. In a sense that there we just see the few evidences of this topologies play some of the important role of the experimental observable. But full understanding of this type of the structures, or even further, there's a possibility we can engineer those kind of topological networks into this twisted Van der Waals system, which actually can be still kind of a lot of things to explore. That's kind of one last remark that I want to make. And thank you very much for your attention.
I think we have maybe more time. You want to sacrifice lunchtime for more session?
You better not.
Let's start this first.
Is that the question? Is it possible to induce this type of dislocation, through engineering?
Yeah.
Forget about twisting. I just want to induce this semi-structure just by engineering.
So it could be very interesting that there is a kind of detailed math that you can do that if I have the sample and say twist it, can double layer sample. Let's say I start with the 2 graphene layers, even bonus second graphene layer. And I have this boundary that let's say that I just start engineering the dislocations, right? I'm shifting this one, right? And I can encode that RGB, GBR, whatever things kind of across this one. And that basically completely dictates how many the vortices or anti-vortices are in the system. So that can be done. Now, experimentally, can I just engineer this dislocations in there? So this is related with surface engineering, the substrate engineering. So if I just give you the relative strain to the system, that's a way that I can engineer. So imagine that I have some sharp surface structures put these double layers on the top of them and just try to give you some level of strain, shear, or that is longitudinal strain, or isotropic strain, or whatever things by the substrate. There's a way that I can engineer that is this location. Indeed, so I think that could be interesting directions. It is indeed kind of really cool that by controlling the boundary condition, boundary dislocations that I'm just going to inject in, I know that what's going on inside. That's basically gives us the experimental control of the topology.
And another question is that because these are really non-orbiting objects, anybody try to proximate it superconductor and can see whether you can get some sort of non-orbiting virus here?
Yeah, so that's also an interesting point that I want kind of distinguish a little bit that this is indeed a non-orbiting, although I have to still kind of lingering around. I have to prove that RL versus LR is different. If you believe me, this is a non-orbiting in terms of structure. Right? This doesn't necessarily mean that some of the non-orbiting in terms of electronic, the quasi-particle nature. So there's still kind of whether this is any this are the non-orbiting atomic lattice structures, defect structures. However, some of the interesting electronic properties, that's yet different separate question. Right?
Yeah, but we can move them to just speak to each other, right?
So if you just think about this, this is non-orbiting object. I think this is interesting things you can do. What is the meaning of this braiding, these things? So the way that you can imagine that is, I have that it's a two vortices, right? Just kind of try to braid. This is a structural vortices which actually always tied with this location line, right? And you cannot break this location line, which means when I braid, I will just kind of drag all these kind of vortex lines around, right? Make the complicated structures there. So often that it turns out in the soft condensed matter area that in liquid crystal, people already see they have very similar structures that kind of often comes with an non-orbiting vortices that can create this the liquid crystal. And often they say that this the topological defect has an umbilical cord behind of that. So when you just kind of braid them, they start getting entangled in this umbilical cord. That wall is basically replaced by the location line of actually this
I first want to say thank you for both talks. I had a quick question regarding the two generators. So could you please go to that slide?
Yes, okay. You guys actually are taking my weak spot. Gee, yes, I shouldn't bring that. But okay, good. I think, yeah, let me see whether I can remember what I learned from my mathematician friends, but I'm sure that, yeah, I can remember if I choose. Yeah, okay. Good. Okay, here we go.
So if you were on the AB point and you wanted to go to the BA point, you could go via R. But is the inverse of R defined on AB?
Yes. Okay. So depends on the inverse of R. I think R is defined, but AB R A where do you have? Okay. AB goes to BA. This is an R, right? If I just move it the other way around, from BA to the AB, that's inverse of R. That's basically the definition.
So if I have like in that diagram there where you have AB, BA, you have the red arrow going from AB to BA. Is the inverse still defined for R?
R inverse.
Yeah. So if you were to start from AB
to the BA, that is R.
That's R.
Yeah. But if I just go in this way, that's R inverse.
But if you I guess.
So all of the RGB is defined that starting from the AB to the one to BA. Right. So that's kind of the notations we use. Right. The reason RL and LR look like the same in here, by the way, is this is just to look at this. I would say configuration space. If you just draw the same parent into the real space, In fact, there are different kind of rules that we can just kind of use. I think that's probably the answer. I need to kind of draw that into the real space diagram. Okay, by the way, okay, good. I think, Emma, did I answer that?
Yeah, I guess so. Really quickly,
yeah.
If all the operations are defined from AB to BA,
yeah,
does that mean that when you go to check if these two groups are abelian, they'll just start on, or excuse me, if these two generators are abelian, just start on AB and then proceed with all the operations?
So let's see that R, G, B are different elements now, right? And then can I create the abelians out of this one? I think statement is basically I say that RL versus LR physically is kind of different incarnations of your space. Therefore, that I will just kind of impose a non-abeliance out of that, right? Of course, if I just make the RL and LR is different, then I think right. With that, I don't think that I can just kind of assign as a RGB as the dislocations with the different Vogel's vectors on the top of that. I don't know whether I answered this question. Yes.
Thank you.
I have a physics question on the.
Yeah. Good, I like that.
Well, you see multiple peaks seems to be periodic in gates on this lines, right? Do you have explanation on that?
Yes, roughly. I think that the peaks that we see in the not only zero but the boundaries, when you just look at the Moore events coming from there, that there was that kind of old event, right? And then there's a lot of this the band of singularities appears into the or the band edges that appears into the your Moore event, and that basically kind of there's a large density of state appears more or less correspond to peak positions of the what we are seeing.
So those are real peaks.
Yeah, that's a real peak. And there's kind of decent match with what theoretic expectations. Right. So we can go back to the math question.
Actually, we have two.
Sure.
So the last question to follow up, I think instead of seeing directly, the easiest way to prove that this is dihedral D3, which has to be non-abelian because dihedral groups.
Say again what?
I was just thinking because the pattern looks very much like dihedral groups. And if you look at D1, D2, those are abelians, and D3 must be non-abelian. So this is why.
Unfortunately, you're talking to the wrong person. All right, so I will just kind of introduce you to my mathematician friends who wrote the kind of this paper together. Yeah. I was fascinated as well. That's why I just.
So, but the second question is a real question, and maybe it's a little bit wild. So there is a Wagner theorem, which basically says for the case of superconductors, if you reduce the dimensionality from 2 dimension to 1 dimension, you break superconductivity.
Yeah.
So I was wondering if there is anything like this in this kind of system, why we fixing the maximum will and then.
Yeah, that's a kind of good point. I think not only is 1D, and the 1D obviously more significantly in the 2D, I think in some sense, there's no order state exists in the finite temperature in some sense, right? The usual way here in the 2D in general is basically, well, that you're right. I think, well, there's a continuous symmetry breaking that basically is susceptible for the order fluctuation, but length scale actually increases with the log scale. So any lab scale of the sample, microns, 10 microns, even centimeters, usually there, because of this finite length scale, that the order state can be survived. Now, go to the 1D, I think this becomes a little bit more tricky, right? So I think that it's not the log scale of the breaking is probably power law or something. So that the fluctuation effect becomes quite significant. What is the effect of there? I think there are a lot of people that already study about the 1D system, so I don't have to comment on there. Network system is rather tricky, right? Because in some sense, I think this is infinite network getting to the 2D limits, but in the microscopic detail, I see that it's 1D connections, right? So there's a kind of interesting this crossover between the length scale. I guess that's related with what is the distance between this node, right? with the temperatures and all of these things. So certainly this could be very interesting, intriguing things, right? I showed you the data that somehow with this incoherent sum, more likely explain that why the resistance doesn't change too much, right? That may already have that kind of the truth. That measurement is done at the 1.5 Kelvin. Maybe at the temperature already kind of all this, the delicate coherence is washed out, only this robust feature may remains. So again, that what is really how robust is the length and what is the role of the fluctuation? I think that could be interesting things to explore.
It also could be interesting probably to get the structure, which is the smallest possible, before it starts breaking the superconductivity and apply electric field and kind of force the knots to move. Yeah. So you're basically creating an analogy of a nanowire based on
That's
the
right. Yes. Yeah.
Just people did experiments.
Yeah. But note that again that this network thing that I mentioned is a relatively large twist angle, and typically it's not kind of directly applicable for the most of the here. The school where the twist angle is about 1 degree or larger than that. And lattice reconstruction effect is a rather small perturbations rather than such a strong effect I was discussing.
Yes, I wonder, so if you like explain the in a small angle diagram case,
yeah,
the satellite peaks is like the higher order band gaps.
Yeah.
But can you also think of that as some kind of, if you think in the language of the splitting and like middle section and then conducting edge, I also think that as some kind of interference effect between different edge state and kind of resulting in some kind of blockage.
Yeah, I think some of these features in the magnetic field we can say this. I think did I go the other directions? Oh, I see. I'm going to the wrong directions. Some of this, the field dependence, I think shows that, say, Hofstadter like the features and some of the magnetic field. So if you want to be maximally hopeful, that yeah, I think there are some structures appears there, and that the characteristic area match with this more size and something. There's actually more experiments done by Klaus Enselin's group. They even just kind of have the go of the careful analysis onto the very similar sample, and they claim that they are seeing that some chiral mode type of the out of Bohm effect coming from the plaquettes. So there are some things, but it's at this point the problem here is it's a relatively large size of sample. So this the angular disorder is even more stronger. So getting really uniform arrays and do this experiment was not too easy at this point. Not impossible, right? So basically, experimental result is suffer from a lot of disorders to make the really concrete conclusions. Other than with the loving eyes, I'm seeing some structures there, and they might be related. But we wish to have a little bit more kind of smoking gun type of things, right? Which I don't know whether even theorists tells us some things. Yeah.
It's like another comment. I really like you explained the non-appealing characterized striking a bunch of domain walls.
Yeah.
I wonder if there's similar kind of concept in app, like
I hope that, yeah, I think what the thing part I like is that this is completely unrelated with those anion things, but at least what I learned is out of this one, at least I got I think this is kind of one of the features that perfect lattice, if you just disorder, you get the vortex and anti-vortex in there. And all the dislocation start to entangle there, right? I thought kind of non-abelian anions is always in the quantum mechanics is exotic object, but it's a lattice scale that everything is a kind of classical. I see the visualization. I'm not sure how that is related with the real the other type of non-abelian anion, but at least it was kind of interesting to see some visualization. The connection, I don't know. I think that mathematician should figure it out. Okay, I think everybody's hungry now.
We can move on.
Yeah. Yeah, I know it's lunchtime, but
No, I'm okay. Yeah, yes, yeah.
So one is asking, what is the time scale for the Moore lattice to go to the relaxed states?
So I don't have the slide, but this is the experiment that one of my collaborators doing, that when you apply the electric field, you can also pulse the electric field and see that how this kind of domain wall start to moves, right? So without any pinning, that domain wall moves really fast. I think that this, in other words, the relaxation, so the change with different magnetic field moves fast. It's probably close to probably some sort of sound velocity or some of this thing. Now, in the realistic sample, there's always some of the pinning centers for the domain walls. This could be dirt or some atomic scale of the defect that will slow down this domain wall motions, then slower than sound speed. So it all kind of depends on how fast it relaxes, how fast it moves. It depends on the kind of defect configuration. If there is no defect, this domain wall can move in terms of kind of really speed of the sound. Yeah, because that's kind of how the lattice stuff kind of moves around, right?
So they can be reconstructed in just seconds.
Yeah, it's really fast, right? Yeah. But, yeah.
So there's another question regarding the your first talk, which we don't have time to go to. So yeah, the attendee is asking a question regarding the Hall ferromagnets. Is the skyrmion the lowest energy configuration, or there could be spin waves which are not topological?
Yes. In terms of charge excitation, skyrmion is believed to be the lowest charge excitation. But of course, there's neutral excitations, especially for ferromagnets. And there can be also the magnons or spinons. I think in this case is possible, or magnon is possible, and that depends on the kind of spin direction and textures. It can be very low energy magnon is also possible, right? So usually in the typical spin state magnons require the Zeeman energy to excite it or those kind of things, but sometimes it's much lower than charged excitations. So it's a low energy transport. Thermal transport can be often dominated by the magnons, and there is some signatures people have started seeing those kind of things as well.
Thank you.
Okay, that's Professor Kim again.
Thank you.